Hello everyone. Today's topic about applications of diode application. So practically, a diode you can apply in the rectifier circuits like conversion of AC to DC for DC operating circuit, battery charging circuits, and another simple diode circuits like clipper, clamper. Mostly used clipper clamper are for wave shaping purpose. So protect circuit against overcurrent, polarity reversal, current caused by an inductive kick in early circuit. There are in simple diode circuit we can apply that. And also another special type of diode Zener circuits that's mostly used for regulation purpose over voltage protection, like reference voltage also used Zener diode. So in the first, when you see about rectifier circuit, so now first let's see about stages of DC power supply. So in DC power supply, we have five stages. As a first stage, we can get a power supply. That power supply comes from the Ethiopian Power Authority Corporation, or in our house what we get it, or plug inserted to the wall socket outlet. We get to 20 volts, 50 hertz. So this power supply first insert to the transformer. The transformer purpose is that as used for value change. That value change that is input also AC, output also AC, but also step down or step up type purpose are transform. So our output also the same AC, but a value change. In the second stage, we get a rectifier circuit. So at this stage, we get a diode. So this diode purpose is for rectification of AC input to pulsating DC output. So purpose of that for rectifier or for conversion of AC to pulsating DC. As a third stage for filtering purpose. So filtering purpose using a capacitor or inductor or other passive components. Yeah, capacitor and inductor mostly. Thus pulsating DC change to pure DC. So in the first stage, we can get a regulator. So this regulator we use stabilize our DC output to our the load. So these are the stages of DC power supply. Now we see about rectifier. So when you say about rectifier, the conversion of AC to DC, that is rectifier. So our diode, as you know, it has anode, cathode side. Anode is as P material, that is positive, cathode as N material, that is negative. So the current is pass only in one direction. So at this output, we get a pulsating DC. In our input, when AC input sinusoidal wave, that is changed to pulsating DC. So rectifier we can divide it into three types. Rectifier divided into three parts, but let's see first half wave rectifier and full wave rectifier. So that means what I say three parts, that full wave also divided into two. That is center tap type of transformer full wave rectifier and bridge type of full wave rectifier. So our full wave rectifier can be divided center tap type of full wave, center tap type of full wave, rectifier and bridge type of full wave rectifier. So mostly used in electronics power supply, bridge type full wave rectifier that is popular and high efficiency. But basic rectification is half wave rectifier. So let's see one by one. So during half wave rectifier, we have a transformer is used to step down the voltage input. Also, a rectifier converter is pulse DC like DC diode. It needs one diode during half wave rectifier. A filter capacitor is used to smooth out the pulses. Diode converts AC input voltage to a pulsed DC output voltage. Whenever the AC input becomes negative at the diode's anode, the diode blocks current flow. Output voltage becomes zero. The output frequency is the same as the input frequency. So, because in one full cycle we have get one pulse, so input frequency is the same as output frequency. The diode analysis will now be expanded to include time-varying functions such as the sinusoidal waveform and square wave. The simplest of network to examine with a time-varying signal appears in figure 2.44. Over one full cycle defined by the period of each to forward the average value, the algebraic sum of the area above and below the axis is zero. The circuit of each 244 called half-wave rectifier will generate a waveform Vout that will have an average value of particularities in the AC to DC conversion process. So let's see one by one analysis. So as you see in this circuit, we have a power source, let's say example 120 voltage supply with 50 hertz. Our transformer ratio 5:1, that means step down transformer. So what is the value of secondary voltage in the transformer? As you know, V primary over V secondary equal to 9 number of turn primary over number of turn so secondary. That means first our input supply is VRMS, that is supply voltage, that is effective voltage, so must be changed to V peak. So V peak is equal to root 2 times VRMS. So root 2 times 120, approximately 170 volt V peak. So now let's get voltage secondary. So 170 over V secondary equal to 1 number of yarn 5 over 1 number of the ratio 1 5 over 1. So let's close. So that means V secondary 170 out to 5, that becomes 34 volt V maximum, or yeah, V maximum is secondary voltage. So this means it has 34 volts. So what about in after the diode our V peak? Now let's see one by one. During forward time, our diode conduct. During reverse time, our diode blocks. So during forward time, our positive is anode side, negative is cathode side. So current pass through the diode. So during this condition, our voltage output becomes positive side becomes in the outside. So V out is equal to V maximum sine omega of t. From where to where? When 0 less than or equal to omega of t less than or equal to pi. But during the reverse time, let's see this one as a negative, this one as a positive. During this time, our diode becomes blocked, so open circuit. So our output becomes 0, V out becomes 0, yeah, that is the same, V out becomes 0. From where to where? From pi less than or equal to omega of t less than or equal to 2 pi. This is the limit. So during reverse, our output becomes 0. So that is a reverse condition of our diode. D1 becomes a reverse condition. During forward from 0 up to pi, diode conducts, that is forward condition time. So in one full cycle, we get one pulse from 0 up to pi. That is, we get V maximum. So what about the value of average voltage? That the value of average voltage means that the DC voltage. What about VDC? So our VDC in our load must have analyzed. Let's show you. V average equal to VDC. VDC means area of the curve over the base. That means our full cycle, that is our area over the base, that is our 2 pi. So VDC becomes the integration from 0 to pi V out d of omega t over 2 pi. When you expand this derivation from 0 pi V out d of omega t plus from pi out to pi V out omega of t. Then that is all 2 pi. Then now our constant number 1 over 2 pi as integration from 0 up to pi. V out means from 0 up to pi is V maximum sine omega of t d of omega of t plus that from pi up to 2 pi V out means that is 0. So during this one, this output becomes 0. It remains 1 over 2 pi integrate from 0 up to pi V maximum sine omega of t d of t. So our constant out from this one from 0 up to pi V maximum over 2 pi sine omega t d of t. So the integration of sine of omega t, as you know, is negative cos theta. So VDC is equal to Vm over 2 pi integration of that is negative cos omega of t from 0 up to pi. So from this we can get minus cos of pi that minus 1 minus of cos of 0 also minus 1 minus plus Vm over 2 pi. You can get 2 by 2, that's equal to Vm over pi. So our VDC is equal to V maximum over pi. That means when you want to divide by 0.318 V maximum. So our V average equal to VDC is equal to 0.318 of V maximum. So by that means VDC we can get, that means V maximum over pi or 0.318 times V maximum. So what about PIV, that is peak voltage during reverse time? During our PIV, that is the voltage on the diode during the reverse, that becomes PIV. It is similar to with V source. PIV equal to with V maximum during the reverse time. And also we can get VRMS in the output. So you know that VRMS means root mean square, so area of the curve of the base under the root. So the result we can get the VRMS, that is half wave VRMS during half wave called V maximum over 2. When you drive from the source, that is area of the curve over the base under the root, then the result you can get V maximum over 2. And also F out equal to F in during half wave rectifier, because during that full cycle we get 1 pulse. So our frequency during pulsating DC is the same with input frequency, that means 50 hertz. So let's see, continue our example. What about VDC? Let's see ideally and practically. Ideally, diode, that VDC becomes 0.318 of Vm. So that means 0.318 times V maximum 34. This result becomes 0 times almost 10.8 VDC. That is in the resistor that we get 10.8 voltage DC. When practically when using practical diode, as you know, the diode has manufactured with silicon, that the silicon diode voltage drop is 0.7, that is parallel potential 0.7. So what we do, our VDC becomes 0.318 multiplied V maximum minus that of VT. So that means 0.318 multiplied 34 minus 0.7. So this result 0.318, that becomes 33.3. So practically, when using practical diode, 0.318 times 3.3, that's approximately 10.5 VDC. So our VDC from this one, when we calculate, that's almost approximately 10.5 voltage DC. So this is the analyzing of half wave rectifier. So where they apply rectifier, that's basic for rectification purpose, but mostly use it, as I tell you, bridge rectifier. So the next we'll discuss about full wave rectifier.